Okay, so today we're going to cover a little bit more about the unit circle. I just want to reinforce some of the ideas that we've originally covered in the last couple days, as well as give you guys an opportunity to get a little bit more practice for yourself. So here's today's plan. Before we start, I just want to give you a really important update on this. From here on, we're going to rely more on the questions and examples in the note booklets that I've uploaded to our Google Classroom. These note booklets should be familiar to you because they were the ones that I was printing off before the entire class cancellation thing started to happen. But we didn't print one off for chapter 4 because I wanted to start something new, and then of course this all happens, so it's kind of a big gong show, right? I want to let you know though that the answer keys to those booklets are also posted. So all of the booklets for each chapter from here on, and again it's chapter 4 all the way to chapter 11, they're posted on the Google Classroom. Answer keys are also posted. If there's anything weird in the answer key, like if you're like, hey, is this actually right? Please let me know, because it's very possible that there could be some things incorrect with them. I filled it in myself a couple of years ago, but I didn't have time, of course, with this whole situation that's going on right now to update them. But anyway, enough rambling. Those notebooklets are very long, and with online learning, we won't have enough time to go over everything in them. So I'm going to pick and choose just some of the things that are in there that I think are going to be important for you going forward. Now, you're free to use the whole original booklet as a reference. Please, by all means, download them. If you have a printer and you're really willing to print them off, then go for it. I wouldn't suggest it, to be honest, but it's up to you. However, you may also take some notes along with this video if you wish. So on a separate piece of paper in your binder or in a quill book or something, whatever works best for you. I'll leave it to you to decide how you are going to be taking notes and making sure that you understand this course. I'm not going to dictate that to you, of course. But for today, what we're covering is we're covering filling in a unit circle, as well as the relationships between angles and coordinates on the unit circle. So when we fill in this unit circle, this isn't really, it sort of is in the booklet. There's one page, but it's not a very good one. I'm going to use that one that we used as a practice guide before the class cancellations. That's what I'm going to fill in. But then we're going to do some questions right out of that booklet, relationships between angles and coordinates on the unit circle. Anyway, enough rambling. Let's get started. So here's a totally blank unit circle. I'm going to kind of narrate this as I go through this and tell you my ideas for how I like to do a unit circle and fill in the whole thing. Now, before we do this, the whole reason we fill in a unit circle is so that we have a very quick and easy reference guide to come back to whenever we deal with any of the ratios or coordinates that may exist on the unit circle. Again, the reason that this is important is because 30, 60, 45-degree right triangles, they're very common and they're very useful for applying to different situations when you're dealing with coordinates on a unit circle. So let's fill this in. Just to let you know, on these dashed lines that are right here, we're going to put the angle in degrees, and on these flat solid lines, we're going to put the angle in radians. I'm going to start with degrees because I think that's a lot quicker and easier. So right here, of course, that would be 0 degrees. This one would be 30 degrees. This one would be 45 degrees, 60 degrees, and of course, 90 degrees. Those are all of your special triangles, right? So it's easy enough to get those started first. Now let's go a little bit more advanced. Let's move on to quadrant 2 over here. This angle, of course, would be 180 degrees because it's half a circle. This angle right here, though, notice it's coming up 30 degrees away from that 180 degrees. So really, it's like we're going to take away 30 degrees from this to make it 150 degrees. Same with this one, it's going to be 45 degrees up from it, so we'll minus 45 degrees from that, and that'll give us 135. Same with this one, we'll need to take away 60 degrees, so that gives us 120 degrees. Then I'll move on to quadrant 3. Notice this one is 30 degrees more than 180, so 210. This one would be 45 degrees more than it, so it's 225. 60 degrees more than it would be 240. And then, of course, 90 degrees more than it brings us down to 270 degrees. As for this final quadrant, some people are often tempted to go off of this one, which you can. I just don't like doing that. I prefer to go off of the x axis here. This dotted line right here is going to be a full circle, so 360 degrees. This next one coming down here is going to be 30 degrees less than that, so it'd be 330 degrees. Need to take away 45 degrees from here to get this one, 315 degrees, and then 60 degrees away from it to give us 300 degrees down here. The next thing I'd like to do is fill in the radian measures, okay? So radian, of course, just another way of measuring angles. We'll start with the easier ones. We'll say this one right here is 0 radians. Hopefully that makes perfect sense to us. And you know what, the next one I'll do is this one here, because we know a full circle in radians is 2 pi, okay? Now, ideally, we want to make sure that all of these different angles in radians are all based around pi. So half of a circle, if a full circle is 2 pi, half a circle is going to be half of 2 pi, or in other words, just 1 pi, right? Then from there, what I like to do is I say, okay, if that's 1 pi, then half of that would logically be pi over 2. And then half of pi over 2 would be a quarter of a pi, or pi over 4. As for these other ones in here, what you're going to need to see is, because remember this was 90 degrees and this was 30 degrees, that would imply that this angle right here is 1/3 of this. Well, if you go pi over 2 and times it by 1/3, that's going to bring you down to pi over 6. This angle up here is twice the 30 degrees. 30 degrees times 2 is 60 degrees, of course. So if you times this by 2, you would have 2 pi over 6, but 2 pi over 6 simplifies down to pi over 3. Notice now that in terms of angles, I have this entire first quadrant done. And what I'm trying to get at here is that your first quadrant is by far the most important one, because if you understand the relationships that exist in this first quadrant, you can just apply them to the other 3 quadrants. Let me show you what I mean. If we look at this angle here, we had 150 degrees because we took away 30 degrees from 180. Well, with radians, you can do the exact same thing, just with pi and pi over 6. If we have pi and we take away a pi over 6, this just becomes a subtracting fractions problem. Remember that pi, like anything else, could be listed as a fraction of any number over the other number plus or times the pi right there, right? So 6 pi over 6 is the same thing as 1 pi. If we're going to take pi over 6 away from that, we could write that as minus 1 pi over 6, which would leave us on the numerator with just 5 pi over 6. That means our angle up here is 5 pi over 6, or 5/6 of a pi. In other words, that's just slightly less than a full pi. So that hopefully would make some sense there. Logically, we can do the same thing with this next angle. We just have to take pi and subtract pi over 4. Well, pi could be written as 4 pi over 4, and if we're taking away 1 pi over 4, that gives us 3 pi over 4. And then lastly, this one up here, it's like we just have to take away pi over 3. So it's like imagining that this pi is a 3 pi over 3, and we're minusing 1 pi over 3 to give us 2 pi over 3. I'll go a lot quicker for the rest of these here. Notice this angle, we'd have to add another 30 degrees, or in other words, add another pi over 6. If this is 6 pi over 6, that brings us to 7 pi over 6. We have to add a pi over 4 to get to this one, so that would give us 5 pi over 4. And then to this one, we'd have to add a pi over 3 to pi, so in other words, that would be 4 pi over 3. As for this 90-degree angle down here, or 270, 90 degrees would be a reference angle, we would have to add another pi over 2. You can imagine this pi as being 2 pi over 2, add another 1 pi over 2, and you have 3 pi over 2. As for this last quadrant, I like basing it around this 2 pi here. These ones are going to be a lot more difficult when it comes to radians, but just bear with me. 2 pi is what we're going to use to base off of this. We'd want to subtract a pi over 6 from 2 pi to find this angle in radians. Well, remember, in order to subtract fractions, they have to have the same denominator. 2 pi could instead be written as something over 6, but you just got to times the top by 6. That would give you 12 pi over 6. And if you're minusing 1 pi over 6 from 12 pi over 6, that means this angle is a really awkward 11 pi over 6. We can continue doing the exact same things with these other ones. Remember, we have to minus a pi over 4 from 2 pi. 2 pi would be 8 pi over 4. Minus a 1 pi over 4 gives us 7 pi over 4. And then for this last one here, we need to subtract pi over 3. Well, 2 pi would be like saying 6 pi over 3. Minus 1 pi over 3 gives us 5 pi over 3. Okay, now we have all of our angles filled in. So the next thing to do is to fill in our coordinates. Let's start with the easy ones, the 4 corners here. This is a unit circle, so we know the length of this line. In other words, the length of the radius of this circle is 1. That would mean our x-coordinate here would be 1, and our y-coordinate is quite obviously 0. Up here, we'd have x is 0, and y is 1. We'd have x is negative 1 over here, and y is 0. And then down here, we'd have x is 0, and y is negative 1. As for these diagonal coordinates, we got a little bit of work to do. And the good news is, this is why we learned special triangles in the first place. Notice right here, you would have a 30, 60, 90 triangle right here. And what we remember, hopefully, is across from 30 degrees. So the y component of this, because across from 30 degrees being down here, across from 30 degrees should give us 1/2. So y should be 1/2. And as for x, it's going to be that really weird √3/2. If you've forgotten how these special triangles work, I highly recommend you go back and look over that again, because I am just relying on the fact that we've already derived these and we understand what the side lengths are in special triangles. If you don't have that memorized, unfortunately, you're going to have a lot of difficulty with this going forward. So it's important to understand that. With pi/4, we have another weird situation. 45 degrees is nice because at least your x and your y's are going to be the same. Those same numbers are √2/2 and √2/2. As for your 60-degree angle, this is much like the 30-degree angle, except they pretty much just switched around. X is going to be 1/2, and y is going to be √3/2. Now, I'll be totally honest with you guys. When I make a unit circle like this, I often like depending heavily on a visual. With the 60-degree triangles and the 30-degree triangles, I often get like confused which one's going to be which. Well, notice with the 30-degree point, my y coordinate, if you like trace this all the way across, my y coordinate looks like it's about halfway up this full one, right? And that's because it is halfway up the full one, right? So in other words, y needs to be 1/2 here. If you want to go the other way, look at the 60-degree point right here. Notice if I bring that down to the x-axis, that looks like it's at about halfway through the x here, which it is, of course. So x is 1/2. Now, getting your first quadrant set up with coordinates, believe it or not, is, in my opinion, the hardest part. Because once you have these coordinates, the other coordinates are going to go really quick. Notice at this point over here, at 120 degrees, this point over here has the exact same height as this point. So we can immediately say this is √3/2. The x, however, just needs to flip and become -1/2. The same applies to all the rest of these. Y is going to be √2/2. X is going to be -√2/2. Y is going to be 1/2 right here. X is going to be -√3/2. Down here, we could actually start relying on these guys. Notice this point has the exact same x coordinate as this guy, so it's going to be -√3/2. And the y coordinate of this is just going to be the negative version of this one, so -1/2. And then follow that through the rest, right? So -√2/2 and -√2/2. And then as for this, it's going to be -1/2 and -√3/2. And then same idea here, keep your x coordinate the same as the one you see up here, so +1/2, but then -√3/2. X will be √2/2 here, but y will be -√2/2 here, and x will be √3/2, but y will be -1/2. And that right there, we've completed the entire unit circle. So make sure you understand what the process is there. Make sure you can understand the whole relationship between the first quadrant, this one way up here, and the quadrants 2, 3, and 4. Okay? All right, now let's do some problems here. These are straight out of the work booklet that I have for you. It's on page 23. First one, if P theta is a point at the intersection of the terminal arm of an angle theta and the unit circle, determine the exact coordinates of each of the following. This is where that unit circle we just completed is going to make our lives way easier here. Notice that what this is saying is the point at an angle of 3π/4. Well, 3π/4, I can just tell intuitively, it's 3/4 of a pi means you're going to be over here somewhere, right? Because this is pi, this is half of pi. If we're 3/4 of pi, we're actually directly in between those two. If we flip back to that other page just now, we can see that at 3π/4, this right here is our coordinate. So in other words, we can say immediately, because we've already done that work, that our exact coordinate is going to be -√2/2, comma, not negative here, sorry, positive √2/2, right? So if I go back to that, we can just confirm, yeah, -√2/2, positive √2/2. So we're good. This next one, I don't like how they've done this here, -π/6. When you have a negative angle, that just means you're going clockwise rather than counterclockwise as you usually would. -π/6 just means you've gone down into quadrant 4 by π/6. If you look back at this, going down into quadrant 4 by π/6, would be this angle right here, the 11 pi over 6. So those would be coterminal. In other words, they have the same terminal arm, they just have a different angle value, right? Notice though the coordinate, root 3 over 2, negative 1/2. So we can just say root 3 over 2, negative 1/2. And then lastly here, 5 pi over 3, that sounds like it's like more than 1 pi, but less than 2 pi. If we look back at our unit circle to save us some trouble, 5 pi over 3, oh, here it is, right there. That's our coordinate, 1/2 and negative root 3 over 2. So we might as well write that down, 1/2, comma, negative root 3 over 2. See how much easier this gets when you have a unit circle already put together? The whole point of creating a unit circle for yourself is so that you can actually access all of these points really quickly, really easily. All right, moving on. Next question, it's also on page 23. Determine one positive and one negative measure for theta if p theta is that. You can go back to your unit circle if you wanted. I'm going to just give myself a little bit of extra work here. We know that this is on a unit circle. Or actually, it doesn't say that it's on a unit circle, but the ratio here for an angle is always going to be the same. So even if this wasn't, we'd be fine. But anyway, negative root 3 over 2, 1/2. This is where it's really going to shine that I show you, oh, that whole thing. Y is 1/2. Okay, there's 1/2 is here. We're looking over here. All right. And the reason it's in this quadrant is because x is negative, but y is positive. Anyway, drawing a line to connect it, even just visually, that looks like it's about 30 degrees. It didn't tell us in this question whether we had to use degrees or radians. If we have 30 degrees here, though, we can say that that's 180 minus 30, or in other words, 150 degrees. So 150 degrees would be one positive theta that we have. For whatever really silly reason, though, it wants us to give a negative measure of an angle as well. Well, this is just the idea of coterminal angles, right? So with coterminal angles say that every single angle that is 360 degrees or some multiple of 360 degrees away from another one is going to be coterminal. It's going to occupy the exact same spot. So why don't we find a negative measure of theta by just taking 150 and minusing 360 from it? So if I threw this in a calculator really quick, because I don't really feel like doing mental math at the moment, that gives me my negative theta is negative 210 degrees. So there's a positive measure and a negative measure, right? And again, I just did this visually, right? I just knew by drawing a picture that since y is 1/2, it's going to be halfway up here, and I can identify just visually that looks a lot more like 30 degrees. If we had instead said that x was 1/2, like over here, if x was 1/2, then that would put our spot on the unit circle up there. That's certainly a lot more than 30 degrees. And I'd go, oh wait, that must be 60 degrees, because I'm aware of what special triangles are. Anyway, next up. Angles on the unit circle, page 23. Okay, so we have two different points on a unit circle. If the object rotates counterclockwise from point A to point B, through what angle has it rotated? Express your answers in radians as an exact value. Okay, so this one's kind of interesting. I'll draw a little bit of a unit circle here. Not a fully labeled one, of course, but just a unit circle here as best I can. A is going to be negative 1/2, and then y root 3 over 2. So, okay, negative 1/2 is about here. Root 3 over 2 would be way up here. I'll label that point A and draw a line to it, okay? Even just visually, you can tell that that's going to be 60 degrees down here. But again, it does want it in radians. We should just know that 60 degrees is pi over 3 radians, okay? So this is where we're at right here. B, on the other hand, is going to be at root 2 over 2, root 2 over 2, which is right in the midpoint here. That's with a 45-degree angle, or in other words, a pi over 4 angle, right? Because pi over 2 is 90 degrees, pi over 4 is 45. It's saying that it wants us to rotate counterclockwise from point A to point B. So we're going to go the other way here, counterclockwise. Wow, okay, so that's going to be quite interesting. Here's how I would personally do this. I would break it into chunks. If you're going to go counterclockwise from A until you reach where B is, you're going to have to take this pi over 3, because that's how far you're going to have to rotate to get to here. Then you want to get all the way over here, so you'd be rotating another full pi, so plus pi. Then you're going to be rotating this last little bit here to get up to B, which would be plus another pi over 4. Hopefully that makes sense. I'll just repeat it one more time. you're going to want to rotate from this point to your x-axis, which we can tell just by special triangles that would be pi over 3 radians. Then from this x-axis to the positive x-axis over here, which would be 1 pi, because it's half a circle, and a full circle is 2 pi, so it's 1 pi. That's what I wrote there, plus the pi over 4 to get it up to where B is, because B, of course, occupies that 45-degree location, or in other words, the pi over 4 location. Adding this together right now doesn't make much sense. We need to have a common denominator between 3, 1, and 4. I think a good common denominator would be 12. That would give us 4 pi over 12, because I times this whole 1 by 4, of course, plus times this whole 1 by 12 would be 12 pi over 12, plus times this whole thing by 3 to turn it into 3 pi over 12. There we go. 4 pi over 12 plus 12 pi over 12 plus 3 pi over 12 is going to be 4 plus 12 is 16, plus 3 is 19 pi over 12. And ideally, we'd like to reduce that, but I don't think we can. There's nothing that's going to divide all that by, so that right there would be our answer. Perfect. Moving on. Last question here. The point T, which is some really awkward decimals there, lies in the unit circle. Determine the value of theta, where theta is the angle. It's supposed to be angle, of course, made by the positive x-axis and the line passing through T. One last time here, I'll draw a very cheap unit circle. X is negative, Y is positive. That Y is almost 1/2. So you know what, I'll just like approximate it right here. Clearly this isn't going to be an exact special triangle here, but we'll do what we can. That looks like that would be the point T right there. We want to find the value of theta, where the value of theta is the angle made by the positive x-axis. Well, that would be this guy over here, and the line passing through T. So in other words, just the normal principal angle. Okay. Bottom line is here, there's a couple different ways of doing this. Personally, I would just use inverse trig on this one, right? Hopefully what you understand is that when you look at this coordinate as if it was part of a triangle, a right triangle right here, your x is going to be the adjacent side to your reference angle, and your y is going to be the opposite side to your reference angle. So you could either consider, with this being your x and this being your y, that if you used cosine, because cosine is adjacent over hypotenuse, and hypotenuse, because it's on a unit circle, is 1, you could use cosine to figure out x, or you could use sine to figure out y. Now my advice here though is never use inverse trig on a negative number. I think in my answer key I actually did use inverse trig. I don't have it open right now, but I just seem to remember when I looked at it earlier today, I was like, ooh, you used inverse trig on a negative number. That was kind of like dicey. But here's what I mean. If you use cosine of theta, cosine theta equals x, your adjacent, over your hypotenuse. That would give you x over 1. And we know x is negative 0.8829 over 1. If you use inverse trig on a negative number, sometimes it will give you the correct answer, but the other times, of course, it can give you something that isn't fully accurate. And what I mean by that is, notice that x would be negative 0.8829 over here as well, right? But that would clearly be a different angle. So if you used inverse trig on negative 0.8829, it's only going to give you one type of angle, and you'd have to use a little bit of intuition to tell you whether or not you've done it correctly. So what I do instead, long story short here, is I always just turn any negative numbers into a positive, and then I recognize that that's my reference angle, theta r, instead. And then I can just use my understanding of the different quadrants to fill in the details from there. So what I'm going to do is I'm going to say cosine theta equals positive 0.8829 over 1 instead. And if I use inverse cosine on that, 0.8829, just doing inverse cos on this, that gives me almost exactly 28 degrees. So close that I'm actually just going to round it right to it. So theta equals 28 degrees. But clearly, because we're in quadrant 2, theta isn't 28 degrees. This is your theta r, your reference angle, right? With a reference angle of 28 degrees, we can just take that away from 180. So I can go 180 minus 28, which should give us 152 degrees as being our true angle. If you don't want to use cosine here, you don't have to. You could also use sine, because notice sine of this reference angle down in the corner here would be opposite over hypotenuse. So you could say sine theta equals y over 1, or in other words, equals 0.4695 over 1. Now that number the y that they gave us is already positive, so we can use inverse trig on that, no problem. Using inverse trig, so inverse sine of 0.4695 equals, what do you know, 28 degrees. That's your theta r, of course. So then we just have to go 180 minus 28. It gave us the exact same answer one way or another. So however you want to go about doing this, it's up to you entirely. I think if you use inverse cos on this negative number, it might actually give you 152 degrees directly, which is great, and that works, and that's a good final answer. But you just got to be mindful that there might be a different answer if you were somewhere else, right? So in other words, just use a little bit of intuition and then ask yourself, hey, does that answer really actually make any sense? All right, so just to recap, special triangles versus unit circle, this is on page 24 of that booklet. Both serve the same purpose, and that's to determine exact values of trig ratios, blah, blah, blah. What is one limit to the unit circle with regards to finding a trig ratio? How do we deal with that? I think what this is referring to a limit of a unit circle is the fact that the radius, or in other words, the hypotenuse, is always 1. How do we deal with that? Just multiply your coordinates by the new radius. In plainer English here, I'm just like trying to save some time here. In more plain English, if you had a circle that wasn't a unit circle, but was rather a circle with a radius of, let's say, 5, you could just take all the coordinates that you know on the unit circle and literally times all of them by 5. It's going to scale just fine. That's another reason why we use a unit circle with a radius of 1, because any of the relationships that we see on that in terms of side lengths, or in other words, coordinates, they can just be scaled. Just multiply them by whatever your radius is, right? Next one, what is one limit of using special triangles? That, to me, like, I'm not sure really what they're asking there, but I would say the limit is really it only works for 30 degrees, 45 degrees, and 60-degree angles, right? We don't have special triangles which would produce exact answers for other angles, at least not handy. I'm sure there are some relationships that exist. We could probably find them ourselves, but for the purpose of this course, that was weird. For the purpose of this course, we can only use those kind of angles, right? And remember, those are your reference angles. So in other words, coming off of your x-axis one way or another. Anyway, to summarize the whole thing, this is some stuff from previous days. The equation for a unit circle is x squared plus y squared equals 1. Really, it should be 1 squared, but remember 1 squared is still 1, so who cares? It can be used to determine if a point is on the unit circle or to find one coordinate given the other, blah, blah, blah. So in other words, don't forget that this is a thing, right? This can come around when you least expect it. If I'm asking you, hey, is this coordinate on the unit circle? You got to use this, right? You can't use other things. You just got to use this. At least this would be the easiest way. On the unit circle, the measure in radians of the central angle and the arc subtended by that angle are numerically the same. In other words, when you have a unit circle, your angle in radians is your arc length. That's all that means. Special triangles can be used to find coordinates of points in the unit circle. Hopefully you know that. We've done that literally this whole lesson. The x-coordinate to every point in the unit circle represents the cosine ratio of that angle. Kind of important to know. That's for x-coordinates, of course. The y-coordinate is the sine ratio of that angle. To find the tan ratio of an angle, divide the y by the x. You might use that, you might not use that, whatever. There it is, good to know. Okay, so that's it. So for practice, I want you guys to go over page 186, questions 1 to 6. We're going to go over these together in the Zoom meeting on Thursday at 10 a.m., so please be prepared. Just another thing, you might want to play that online unit circle game a few times. Again, it's really good just for getting some unit circle practice. And the other thing I want to remind you guys is please check your email, okay? I've been sending emails out just about checking in whether or not you're understanding some of the content that we've been covering. This is going to be happening 3 times a week from here on out. And when I send an email, you need to be responding to those emails as well, okay? So when I send an email out and say, hey, how are you doing? Send me a response back. Even if it's just a, yeah, I'm understanding this, it's good, whatever. That's all I need to hear from you. If you do have any questions, though, that's your opportunity to ask. Anyway, again, check your email, respond to the email, and make sure you do these questions that I posted at the top of the page. Talk to you guys soon.